Welcome to all of you in Sankalpa Education Pratham classes. I am Sachin Patil, delivered lecture series on rotational dynamics. Right now we are going with angular momentum. It is a rotational mechanics. It is a quantity in rotational mechanics. It is quantity in rotational mechanics and analogous to linear momentum and it is also called as moment of linear momentum. It is denoted by L. It is denoted by L, capital L, and it is nothing but it is its instance where later to consider. First of all, we have to later to consider here. Let P bar is instantaneous linear momentum of a particle perform circular motion. Then we have to get the consideration of angular momentum, and therefore angular momentum it is equal to L bar is equal to R bar cross P bar is here. P bar is nothing but a linear momentum, or it is an instantaneous value of linear momentum, and R bar here R bar is radius vector from axis of rotation is here, and at that time you will get it is a position vector. Also, it is also called as a position vector or radius vector from the axis of rotation, and it is a particle which is moving in a angular momentum or moving in a circular path along the radius or radius vector, and at that time you will get the consideration of its magnitude is considered as L is equal to PR sine theta, where theta is angle between P bar and R bar is here. This is your definition related to angular momentum. What is angular momentum? It is one quantity in rotational mechanics, and which is analogous to linear momentum also, and it is also called as a moment of linear momentum. If you will get the P bar is an instantaneous linear momentum of a particle which perform the circular motion, at that time you will get the angular moment is equal to L bar is equal to R bar cross P bar, and according to cross product we have to get the magnitude of that angular momentum. L is equal to P into R into sine theta, where theta is the angle between P bar and R bar is here. And right now we are going with the next point related to that one is nothing but a expression for angular momentum. Expression for angular momentum in terms of terms of moment of inertia. In terms of moment of inertia, how it is calculated, the moment of inertia in terms angular momentum in terms of moment of inertia. First of all, we have to going with the consideration of one body, and this body consists of number of particles. Let us consider one object. Let object rotates with constant angular velocity that is omega is there, constant angular velocity, and it consists n number of particles of masses m1, m2, m3 and so on up to mn, and it performs and those particles are at distance r1, r2, r3 and so on up to rn from axis of rotation. At that time you can calculate the first of all linear velocity related to that particles, and you have to perform the consideration related to angular momentum in terms of moment of inertia. First of all, you have to get the diagrammatical representation of this one as follow. Let you to consider this diagram. Inside this diagram you have to get the consideration of m1, m2, m3 and so on up to lot of masses are there. Let you to consider m1 be the mass here, m2 be the mass here, m1 be the mass at distance r1, and moment of linear momentum is a p1 at that time. Let m2 be the mass at distance r2, and p2 be the moment of linear momentum at that position. Let us consider mn be the mass at a distance rn from the axis of rotation, and pn be the linear momentum at that time. And we have to get the consideration of this is the moment of inertia, linear momentum related to that one, and you will get the consideration of first of all we have to carry out the we know that linear velocity related to that particles, it is done by using angular velocity and radius vectors. From that consideration, let us consider this body is rotated about that axis passing through point O, and you will get the all particles perform the circular motion, and p1, p2 and so on up to pn are the moment of inertia, linear momentums at each particle, linear momentum of each particle. First of all, we know that V is equal to r omega. We know that this formula is nothing but what? Linear velocity is equal to radius vector or radius into angular velocity. Right now angular velocity is omega, and it is constant related to that object which is rotated about that axis of rotation O. And right now we have to get the consideration m1 be the particle at a distance r1, and p1 being the linear momentum is there. Right now first of all we have to get the consideration of V is equal to r omega, and therefore velocity of first particle, that means linear velocity of particle of mass m1 is v1 is equal to r1 omega. Similarly v2 is equal to r2 omega, v3 is equal to r3 omega, and so on up to you will get the consideration of Vn is equal to Rn omega is here. And those are the linear velocities related to that particles which is having the masses m1, m2 and so on up to mn is there. Right now we know that the linear momentum is equal to mass into velocity, and therefore you will get the linear momentum of first particle. That means the linear momentum of mass of particle of mass m1 is let it consider it is a p1. It is a p1 is here, and p1 is equal to m1 v1. But we know that the v1 is nothing but what? v1 is nothing but r omega, and therefore you will get the m1 r1 omega is here. Similarly p2 is equal to m2 v2, but v2 is nothing but what? We will get the consideration of m2 r2 omega. p3 is equal to m3 v3, and therefore you will get the m3 r3 omega, and so on up to pn is equal to mn vn, and therefore mn vn, and therefore you will get the mn rn omega is here. And those are the linear momentums or instantaneous linear momentums at that time. Right now, by using angular momentum, we know that the angular momentum, and here first of all we have to get the consideration of angle between these p bar and r bar. First of all you have to clear the consideration related to that one, and you can calculate the angular momentum at each angular momentum of each particle, and by using that one you can calculate the consideration of angular momentum in terms of the linear momentum is angular momentum in terms of the moment of inertia. We know that the linear momentum angular momentum is given by P cross R into sine theta is here. That means P into R. P is nothing but a linear momentum, and R is the distance from the axis of rotation. Right now, first of all, we have to get the consideration of P bar and R bar. Theta is the angle between P bar and R bar. Here, R bar is nothing but this radius vector is here, and P bar is nothing but this vector, and angle between these two is nothing but a 90 degree. Angle between these two is nothing but a 90 degree, and theta is equal to 90 degree, then sine theta is equal to 1, and therefore you will get the L is equal to P into R. Once again I am repeating here, first of all, linear momentum P bar and radius vector R bar, or distance from the axis of rotation is R bar, and the angle between these two is nothing but a theta, and here theta is nothing but a 90 degree between these two. That means radius R1 and P1, R2 and P2, Rn and Pn is here, and you will get the theta is equal to 90 degree. If you put the theta is equal to 90 degree, sine theta is equal to 1, and therefore L is equal to P into R is here. By using this consideration, you can calculate the considerations related to each particle and angular momentum of each particle. By using angular momentum of each particle, you can calculate the angular momentum in terms of the moment of inertia as follow. Right now, from figure you will get the consideration of theta is equal to 90 degree, and it implies that sine theta is equal to 1, and therefore L is equal to P into R sine theta, where sine theta is equal to 1. It becomes L is equal to P into R is here, and therefore by using this consideration, angular momentum of particle of mass m1 is L1 is equal to P1 into R1, but we know that P1 is equal to M1 R1 omega. Putting this value inside this one, you will get the L1 is equal to M1 R1 omega into R1. R1 into R1, you will get the R1 square, and therefore L1 is equal to M1 R1 square omega. Similarly, you will get the consideration of similarly L2 is equal to M2 R2 square omega. L3 is equal to M3 R3 square omega, and so on up to you will get the Ln is equal to Mn Rn square omega is here, and therefore angular momentum of object is equal to summation of angular momentum of particles. Here n number of particles, therefore you have to take the consideration of I is equal to 1 to n is here, and therefore summation I takes value 1 to n m I r I square omega is here. Now putting the I is equal to 1, you will get the M1 R1 square omega plus summation is nothing but a plus. I is increased by 1, you will get the M2 R2 square omega plus M3 R3 square omega plus, and so on up to you will get the Mn Rn square omega, and those are nothing but L1 plus L2 plus L3 plus, and so on up to Ln is here. And by using this consideration we get the angular momentum of that object, and which is nothing but once again angular momentum L is equal to, now angular momentum of object is nothing but L is equal to summation of I takes value 1 to n mi ri square into omega, but this omega is a constant and therefore it is taken outside, and you will get the consideration of we will take the consideration of in a bracket summation I takes value 1 to n mi ri square into omega, but we know that this the value is nothing but moment of inertia, that means I is equal to summation of I takes value 1 to n mi ri square is here, and therefore L is equal to I into omega is here, and this is the expression of moment of inertia, angular momentum in terms of moment of inertia is there. First of all, we know that the consideration of here we will get the note related to that one, how it is calculated. First of all, you have to get the consideration of I is equal to mr square is here. Let you to consider m be the mass of that object, and you will get the consideration of mr square, and omega is denoted, or it is given as v divided by r, because we know that v is equal to r omega is here, and therefore omega is equal to v divided by r, and putting those value inside this L is equal to you will get the consideration of m r square into v divided by r. 1r and 1r is cancelled here, you will get the mvr, but we know that the mass into linear velocity, this value is nothing but a linear momentum, and it is denoted by p into r is here, and therefore this I into omega, L is equal to I into omega, it is a angular momentum in terms of moment of inertia, and therefore it is a angular momentum is equal to moment of inertia into angular velocity angular velocity. This is your expression in words, and you will get the consideration of when we putting I is equal to mr square is here and omega is equal to v divided by r. Inside the equation you will get the consideration of L is equal to P into R, and which is already known to you and which is taken here. L is equal to P into R into sin theta, where sin theta is equal to 1 putting, you will get the L is equal to P into R. This is a consideration. That means these are two equations are nothing but an alternate one. That means when we put the P is equal to M into V and into R, you will get the consideration of I omega is here, and I omega 2, you will get the L is equal to P into R. If you like this video, please subscribe my channel and click on bell icon to get the next notification related to that lecture series related to rotational dynamics. Thank you.